In the previous example, we calculate the electric potential from an electric field without any information of the source of the electric field. We just say that somehow we produce the electric field, parallel electric field. Now, we will look at the case that we know the source of electric field. Maybe the simplest case is that the source of the electric field is a point charge. Okay, so we have a point charge Q here, and in the region around Q, we will have the electric field point outward in the radial direction from Q, right? Because we have that E is equal to the KQ over R square times the unit vector R. This is a Coulomb's law, and R point outward in the radial direction from Q. Okay, we have R like this. Okay, we have R like this. Now, if we want to calculate the electric potential difference between 2 points, A maybe here and B maybe here. Okay. First, let A and B lie along the radial of the line in the radial direction from Q. Okay, it means that you can draw a line start from Q and pass through A and B. So this is in the radial direction. Okay, and I want to calculate the potential difference VB minus VA. From definition, is equal to the integral from A to B of E dot dr. Now, we have to choose the part of our integration. You can see it's quite obvious that the easiest part is the part along the radial direction, like this. So if I define dr point from A to B in the radial direction like this, so you can see that along this path, we must have the E is parallel to dr. Right? Along this path, E is parallel to dr. Because R point in the radial direction like this. E point in the radial direction like this. So, once we have that E is parallel to dr, we have E dot dr is equal to E dr. Okay? So we have that is equal to the minus of integral from A to B of E dr. Okay? Now, E is not a constant vector because the magnitude of E inversely depends on the R squared. So we cannot take R out of the integration as in the previous example. Okay, so we have to put E into our equation, our calculation. So this equal to the minus of A to B of K Q over R squared dr. Right? K and Q is a constant. K is an electric constant. Q is a charge of the source. If we fix the charge, we look at the same charge. So K and Q are constant. We can take it outside the equation. So we have that is equal to the KQ minus of KQ from A to B of dr R to the minus 2 dr. Right? If I take it to on the upper side, write it as a r to the minus 2. To do this integration is quite simple. The integration of r to the minus 2 is equal to 1 to the minus 1, okay, of r to the minus 1. Take the limit from a to b. Okay, this negative sign and this negative sign will cancel, so we have the final result is equal to the k q times 1 over ra, 1 over rb minus 1 over ra. Okay, so this is the result of our calculation. Okay, you can see that if q is positive, and if we move away from q, when we move from a to b, it means that we move away from q. So it means that this is ra, and this is rb. In this case, RB is larger than RA. So when we move away from the charge, the electric potential will decrease, right? Because RB is greater than RA, 1 over RB will less than 1 over RA, and the result is negative. But if we put A here and B here, and we move in this direction. In the case that we have positive Q, the electric potential increase. Okay, we can. This is very similar to the previous example when we have a constant E. You can see that if we move along the field direction, we have that delta V is negative, or the electric potential decrease, right? But if we move against the field, the electric field, in this case, we will have that delta V is positive. This is very similar because you can see that if you move along the field, in this case, delta V is negative. Okay? But if you move against the field, delta V is positive. Okay? This is the nature of the potential, electric potential difference. If you move against the field, the electric potential will increase. If you move along the field, potential difference will decrease. Okay. Also, if we want to know the electric potential energy difference, it means that we have to put the base charge and move it from A to B. So the electric potential energy difference is equal, again, delta U is equal to the Q0 delta V. Okay? If Q0 is positive, you move it against the field will increase the potential energy of the system. But if you move along the field, you have to do nothing. If you go by itself, and it means that the potential energy of the system decrease. Okay.